This is the physical sciences question paper that was written last year. It is the March control test from the Limpopo provincial government, right? So it's a term 1 control test. The marks is 100 and it was for 2 hours. So we're going to try to answer this question paper within that allocated time. An important thing is the instructions. So the first one tells you the number of pages. Always double check to make sure that indeed it is the number of pages that are mentioned. Another thing that is important, check your data sheet. Check that your formula sheet is there because it's supposed to be provided to you. And then another important one is rounding off, and you are told that you need to round off to 2 decimal places. So if you provide your answer to 3, 4 decimal places, you will be marked wrong. An important thing is to show your calculations, especially the formulas. So in physics or in physical sciences, when we write, you get a mark for just giving us the formula that you will be working to solve your problem, right? So let's just go ahead. And before, I think it's important to mention that I downloaded this from stenmorephysics.com. I think that's how it's pronounced. So let's go to question 1. And we can read this question together. So question 1 says, four options are provided as possible answers to the following questions. Each question has only one correct answer. So it has only one correct answer. Choose the answer and write only the letter. So you only write the letter, not the statement, just the letter. So if it's question 1.1 and you see, okay, the answer is C, just write C. You don't need to write anything else from there. So it's just continue. So just write only the letter next to the question number in the answer sheet. Now they have shown you an example, right? So let me just scroll down. So here we are told that I'm trying to remove this. Here we are told that 2 pulses, 1.1, 2 pulses are traveling towards each other along a string, as shown in the diagram below. So we have the first pulse, let's call this pulse 1 or P1, and then we have another pulse 2, call it P2. So you see these 2 pulses are traveling towards each other because this one is moving from left to right and this one is moving from right to left. And if they're traveling towards each other, at some point, let's say at point Q, they're going to meet. And typically when they meet, we say that they overlap. So that's the most scientific way of saying it. They're going to meet or overlap. Now, when they do meet, when the centers of these 2 pulses meet at Q, the amplitude of the resultant phase will be. So we need to determine what the amplitude is going to be when they meet at that point that was indicated as Q. Before we answer this question, it's important, let's say we define the equilibrium. So this point here, we can draw an imaginary line here, and we say that is the equilibrium. So say this is the equilibrium. That is the position where there is no disturbance. So remember, a pulse in physics is defined as a single disturbance within a medium. So we have a disturbance here, that's P1 or pulse 1. We also have another disturbance here. So also note that the distance, let me not say the distance, the displacement from equilibrium to this highest point there. This highest point also has a name. We call it a crest. I hope you remember that. It's a crest. that the displacement there, that change in position, it means the particle was initially at rest and then it jumped up, got to the highest point, then down. So that's why we have that highest point, or the peak, is called the crest. In this instance, you see that this pulse P2 is below equilibrium, and that the lowest point also has a name. We call it the trough. It's the lowest point on a wave or on a pulse, right? So when this happens, when we have a crest and a trough meeting or overlapping, we're going to just minus their amplitude. So we will actually, so it means here we will have, when they meet, we will have this peak, and then it's beating with this one. You see that this pulse is actually larger than this pulse over here. So it means it's going to cancel this one. So essentially we will be left on top there. Let me change the color of the pen to demonstrate, so we can make it red. So why it is stubborn. So now it means that we essentially will be left with maybe a peak, a pulse. I keep saying a peak, a pulse, like that. And its amplitude, this pulse, is going to be y minus x. So it will be this amplitude of pulse P1 minus the amplitude of pulse P2, because we have a trough and a crest. If it was a crest and a crest, we would add, or if it was a trough and a trough, we would also add. But now we actually minus the two amplitudes. So which option there gives us a y minus x? And you see the option that gives us y minus x is actually C. So you actually get your 2 marks. Let's go to question 1.2. Question 1.2, when two wave crests overlap, the increase in amplitude is due to A, cancellation, B, two waves in phase, C, destructive interference, or D, constructive interference. So we're still talking about the crests. So if we have a crest and another crest, and they are going to overlap, that is, they're going to meet, they're going to interfere, they go through something called superposition. And if it's a crest and a crest, we say it is constructive interference. The type of superposition that they undergo is constructive interference. However, as with the question above, you see that we actually have a crest and a trough. So that would actually mean it was destructive interference. But in this case, we are told that it is the crest of one and the crest of another. And when they overlap or meet, they will interfere constructively. So that is how you will get your 2 marks. We go to question 1.3. The frequency of a wave is defined as the lowest point on the wave. That is a lie. It can be this. The lowest point on the wave is the trough. B, time taken for one complete wave. That is a lie. That a time taken for one complete wave is actually called the period. So you see how important it is to know those definitions. C, number of complete waves per second. There we are. This is the answer. So the frequency of a wave, that is something you need to know and to memorize and to understand. The frequency of a wave is defined as the number of complete waves per second. But the frequency and the period, there's a relationship there, and later in the structured questions you will see it. So the answer for 1.3 is C. Let's go to 1.4. 1.4. In which one of the following do sound waves travel the fastest? So A, is it in air? B, is it in liquids? C, is it in solid? D, is it in vacuum? One of the strategies that I like to use for multiple choice question is called elimination. Elimination, whereby I just eliminate or remove the wrong answers as you saw above. One thing about sound is that it doesn't travel through vacuum or vacuum, however you pronounce it. So we know that the option cannot be D. So we are left with A, B, or C. Sound is interesting because it travels faster. My handwriting. It travels faster in more denser denser in substances that have a high density. When I say a high density, it means the particles of that substance or material are packed together. So let's look. In air, the particles are not as packed. So you can just say there's increasing density from air, which is a mainly gas, increasing density, to solid. So in air, the particles are not packed together. So air is less dense than in liquids. However, solids are more dense than liquid and to air. Now, it means that the sound wave is going to travel faster in a solid because the particles are packed together. Solid materials are much more denser than liquid or air substances or materials. So the answer will be C. Sound waves travel the fastest in solids in comparison to in liquids or air. And sound at all, it doesn't travel in vacuum. The only waves that travel in vacuum are your electromagnetic waves. Question 1.5. Which one of the following combinations below concerning the pitch and the loudness of sound is correct? The pitch and loudness of sound depend on. So we are given a table. In this table, in this column, we have pitch. In this column, we have loudness. So the pitch A, frequency, amplitude of vibration. B, frequency, speed of vibration. C, amplitude of vibration, frequency. Speed of vibration, frequency. And again, elimination. One thing you should know about pitch is that it is related. There's a relationship between pitch and frequency. So what does that tell us? It tells us that only these two options, so option C and D, cannot be correct because the pitch is only related to the frequency of that wave. The loudness, one thing you should know, the loudness also sometimes can be referred to as the volume. The loudness is only related to the amplitude. So what does that tell us? It tells us that the option, it means this option is wrong. We eliminated B, C, D, it means the answer is A. So the pitch and loudness of sound depend on in terms of the pitch, is this the frequency? The higher the frequency, the higher the pitch. The loudness, the louder the sound, the higher the amplitude of that vibration. Remember, sound is a form of vibration. Question 1.6. Consider the following statements concerning ultraviolet radiation. Ultraviolet radiation is a form of electromagnetic radiation. 1. It cannot be reflected. So we have a Roman figure 1. It cannot be reflected. 2. It has a longer wavelength than gamma rays. It is radiated from the sun and may be harmful to humans. So now you need to decide A is number 1 and number 2, the only correct ones. Is number 2 and free, the only correct one. I don't know why they wrote this here. Doesn't make sense. I think that was a mistake. And then C is number 1 and number 3. So only the correct ones. Or all of these things are actually correct. 1. So it's very important for you to understand, to memorize the electromagnetic spectrum in terms of how those waves are arranged with respect to frequency or wavelength, so that we can actually be able to, to answer this question. You need to know how they are arranged in terms of frequency F or wavelength. So 1, sound can be reflected. Waves can be reflected. So even electromagnetic waves can be reflected. So already this statement tells us that this is wrong when they say that ultraviolet radiation cannot be reflected. All electromagnetic radiation can be reflected. 1, it has a longer wavelength than gamma rays. So you have your electromagnetic spectrum. If let's start from the one with the shortest wavelength, we have gamma rays, and then you have X-rays, and then you have your UV radiation. So this is in terms of increasing wavelength. It means that gamma rays actually have a shorter wavelength. They have a very high energy, but they have a very short wavelength. So this tells us that UV radiation actually has a longer wavelength than gamma rays. So this statement is actually true. It is radiated from the sun, that is true, and may be harmful to humans, that is also true. So UV radiation can be divided into UVA, UVB, and UVC. And some of this radiation can be harmful to humans if we come into contact with it. So we said that option 2 and 3 are true. So which one is that? It is 1, 2, and 3. So that is actually means the correct option is B. When I was in school, I used to struggle with these types of questions because I could never understand or interpret them. Okay, we are given options and then we still also given options. Yeah. A 1.7. A rod acquires a negative charge after it has been rubbed with wool. So in terms of electrostatics, when you have one material, a rod, and you have another material like wool, and you rub them together, that thing of rubbing them, it's called triboelectric charging. It's one way we can transfer charge from one material to another. Triboelectric charging. Let me just do this. It's triboelectric charging. Okay, so which one of the following best explains why this happens? So you have, let's say this is a rod, and this is wool. So rod and wool. You have rubbed these two materials together, right? And all of a sudden this one has an excess of negative charge. This means that this one will have a shortage of negative charge. Because why? It means that the negative charge was actually transferred from the wool to the rod. Only negative charges can be transferred. Positive charges cannot be transferred because they are tightly bound to the nucleus. When you do chemistry, I think in the second term, you will learn about all of these things. So again, elimination. I've just said positive charges cannot be transferred. Means option A, which says positive charges are transferred from the rod to the wool, is incorrect. Again, option C, that tells us that positive charges are transferred from the wool to the rod is also incorrect. So our options here, our candidates, 2, are B and D. Negative charges are transferred from the wool to the rod. Negative charges are transferred from the rod to the wool. That is not true. We know that negative charges are transferred from the wool to the rod, meaning this will have excess electrons, hence it's negative. There's now an excess of negative charge, and this one, because it transferred its electrons, will have a shortage of electrons, a deficiency. Sometimes that's what they say, deficiency of electrons. So that's why it is now positive. It has more protons than it has more protons than electrons. I almost said neurons. It has more protons than electrons. So this means that option, the correct option here is 1 point. Why am I saying 1 point? Is D. Negative charges are transferred from the wool to the rod. I always like this electrostatic questions. I don't know why. 1.8, a rubber balloon obtains a negative charge after it has been rubbed with against human hair. This is actually the same question as the one above, if you think about it. Which one of the statements below explains why this happens? 1, let's start with eliminations. Positive charges cannot be transferred, so we can eliminate option B and D, or option B and C. And now, what can be transferred? We said it's negative charge. So they say this balloon, this is a balloon, it was rubbed against human hair. So there's your hair, your eyes over there. So you rubbed it, and then after that it obtained a negative charge. So remember, negative charges are the only that can be transferred. It means the negative charges in this instance were transferred from the hair to the balloon. Negative charges are transferred from the human hair to the balloon. So this is the correct answer, D. Let's move on to another question. Two identical light bulbs are connected in parallel, as shown in the circuit diagram below. Voltmeters V1 and V2 are connected across each light bulb. A voltmeter is always connected across. That means it's always connected in parallel to a circuit element. What does that mean? Let me take, so you see, I want to just demonstrate. Let me use different colors. So we can just start from the battery. You see, let's say this is a branch in which that connects the battery and then light bulb 1, right? But we can also see that we can also here can have a separate branch in orange that now connects a light bulb 2, right? That's why, so these two light bulbs, this light bulb and this one, are on separate branches. That's why we say they are connected in parallel. And also take note, because I mentioned that a voltmeter must always be connected in what? In parallel. There is also connected in a separate branch, yellow. So it's not connected on the same branch as the light bulb. Also, let's check the voltmeter below. Like that color. I don't know, is it purple? You see that it's connected on a completely separate branches. So when circuit elements are connected like this, we say that they are connected in parallel. So, and also it is always important to know that voltmeters in comparison to ammeters are always connected in parallel. So we're trying to find what is the potential difference for this light bulb with using this voltmeter V1, and we're also trying to find what is the potential difference in this light bulb using voltmeter V2. That's what we're trying to determine, right? So Another important thing, because they've mentioned that the two light bulbs are connected in parallel, circuit elements, let me see if I can write that. I think I'll type quicker. So something that you need to circuit elements connected in parallel experience the same potential difference. That is something important to take away from this. Circuit elements connected in parallel experience the same potential difference. What does that mean? It means that if now this light bulb, it's a mistake. If now this light bulb, right, and this light bulb are connected in parallel, it means they will actually have the same potential difference. Potential difference is going to be the same because circuit elements connected in parallel have the same potential difference. So what does that tell you? It means that the potential, the voltmeter V1 will measure the same potential difference as the voltmeter V2. So that's why they will be the same. So if we look at our options, we can then say, okay, which option says V1 equals to V2? And lucky for us, it is just option A. Option A, which is that V1 equals to V2. That's how you get your 2 marks. Now, for which one of the quantities below is correct, is the correct unit of measurement given? That question is written in a very cryptic way. For which one of the quantities below is the correct unit of measurement given? It means that they give us the physical quantity, current, energy, potential difference, resistance. And now we need to check against the column for the unit if the corresponding unit is correct. So is the current measured? The current I is measured in amperes. So this means this is incorrect. Energy is measured in joule, J. So this means this is incorrect. Potential difference, yes, is measured in volts. In volts V. So this option is actually correct. And the resistance D is actually measured in ohms. And remember, resistance can be given by V over I. It means it's going to be V over A, not Vs. So the correct option there, as I've mentioned, is 1.10. So we have answered the whole of question 1, multiple choice. Each question carries about 2 marks. So that's why 10 times 2 is 20. It's like 20 out of 100. That's 20% already that you have obtained. Let's go to now the long or the structured questions. Question 2. So question 2 here, you see it's the section that you need to have studied for, which is transverse pulses. Transverse pulses. I'm still learning to use this writing tablet, so bear with me in terms of my handwriting. Transverse pulses in a string or a spring. That is the section, string or spring. Question 2. 2 girls standing at opposite ends of a rope. So we have a girl here and another girl. They are standing at opposite ends of a road. Each makes a pulse of the same speed. So let's call this girl A, makes a pulse A. There's the pulse with an amplitude. So we say the amplitude of this pulse A is 4 centimeters. And this pulse moves to the right. So it's moving to the right. And moves to the right, and pulse B with an amplitude of, I say pulse B has an, let me write AB, can write AA here. AB equals to -6 centimeters. I don't like when they write an amplitude as negative. However, I've seen now the different types of question papers that I've come across that they write a negative amplitude. So because the memo reports this as a negative, I'll just go along with it. But typically, an amplitude is an absolute value. And what I mean when I say an absolute value is that it must always be positive. Maybe in later grades or people that will continue with physics to university, then you'll start to learn that we only take the absolute value, which is positive, for the amplitude. But I don't want to mislead you and saying your amplitude must be positive, but then when you now check the memo, you find that that amplitude was negative, then you will get that mark wrong. So let's just go along with what they tell us. They're saying that AB, which is our amplitude, has a value of -6 centimeters. So that essentially, that negative for them just tells us the direction. So if this direction going up is positive and this direction going down is negative. So, and then the pulses, if they are heading towards each other, B is heading to the left and A is heading to the right, they will meet at some point or overlap at C. What happens when they meet? So there is a phenomenon, as you see with question 2.1. Question 2.1 says, state the phenomenon observed when the two pulses meet at a point C. So what is that phenomenon? So when these two pulses meet, they undergo a phenomenon. Oh, that is English. A phenomenon called superposition. That is when they occupy the same position, superposition. So they undergo a superposition. So that is when they occupy the same position or the same space at the same time. So you will write that they undergo a phenomenon called superposition and you get your mark. And you also, because it's free marks, it tells you don't just mention it, you also need to state it. And that superposition principle says that the algebraic sum, which just means the sum of the amplitudes of the two pulses. Our pulses in this case is pulse A and pulse B that occupy the same space at the same time. So this may feel like a lot of English, but essentially what it is saying is that when those two pulses meet or overlap, they will undergo superposition. And superposition simply means that they occupy the same space at the same time. And then what happens is that their amplitudes will add. So we'll add their two amplitudes. They will add. So we have amplitude. We'll have amplitude. I'm not sure why this is not writing. What did I press? Let me check. So we'll have amplitude A plus amplitude AB when they meet there at position C. That is what essentially when they say the algebraic sum of the amplitude of the pulses that occupy the same position at the same time. That is what is referred to as superposition. So you get your 3 marks, you get a mark for saying superposition, and you also get 2 marks for saying it is the sum of the two amplitudes of the amplitudes of the two pulses. Now draw a labeled diagram to show the resultant pulse when the two pulses meet at point C. Labeled the pulses clearly. So you must include all the pulses there. So I don't have space. Let me check at the bottom. So to draw this, you will say, okay, we have equilibrium, that is the position of no disturbance. And then we have which one has a bigger amplitude. I think it's the one below, which has an amplitude of about -6. So you'll show it by making that pulse look longer. So this is at a point C. And then they occupy the same space or the same position at the same time. So we also have the amplitude of B. Which one? A. So this is A. This is B. But when they do meet, we said that their amplitudes will add. So it means the new pulse that will be produced will have an amplitude. So let's say the new pulse that will meet will have an amplitude that is equals to AB, AA, the amplitude of pulse A, plus the amplitude of pulse, pulse B. So the amplitude of pulse A, they said it is, let me go check. It is 4 centimeters. It's 4 centimeters plus the amplitude of this one, they said it's -6. So we have 4 plus, if you a plus multiplied by a minus, it's just a minus, so we actually just have 4 minus 6, which is equals to -2. So this tells us that the new pulse will also, we said that the position down is represented by a negative and up is represented by a positive. So if this amplitude is negative, it tells us that the pulse will actually be down, facing down. So we have that pulse over there, which is going to just be facing down. So this will just be A plus B. Pulse A plus pulse B. I hope that makes sense. Let's go to the next question. Name the type of interference that takes place when these two pulses meet. So we have, as I mentioned before in multiple choice, if we have a pulse above equilibrium as A is and a pulse below equilibrium meeting, we actually get destructive interference because you'll have the crest of A overlapping with the trough of pulse B. So just write the type of interference. It is destructive interference. And then say question 2.4 says determine the resultant amplitude of the two pulses at point C. I think here, without knowing, I've already demonstrated it. So it's going to be something like that. That's why I said, because they say it's negative, so it's always important to just include it so that your answers correlate to the memo. And now question 2.5. How will the amplitude of pulse A be affected after passing point C? Write down only increases, decreases, or remains the same. So with a superposition, so you said we have a pulse A and a pulse B. They are meeting. This is B, this is A. They are going towards each other. Then here it is they meet. After they meet, they will continue. They will continue in their original direction. So this will be pulse B and this will be pulse A. Continue in the same direction. Remember, it was going to the right. It's still going to the right even here. This one was going to the left. It's still going to the left even here. And also their amplitudes after they have met will be the same. So if this amplitude was X, this amplitude will still also be X. If this amplitude was Y, this amplitude will still also be Y. So it means that the amplitude remains the same because you are asked how will it be affected. So you will just write remains the same, and that will be your answer. Let's go to question 3. Question 3. Question 3 says to us, the diagram below represents a water wave moving from left to right. So this is left, and then it's going to the right. The time between two consecutive crests is 0.5. So it's important for you to know that the time between two consecutive crests, they have actually told us the period t, which is 0.5. Just want to remove that. So this question already tells us that the period, which is the time between two consecutive crests, or the time taken to complete one full or one complete wave, that is the period. Then we're given a diagram of this wave. If we look at it, it's actually a transverse wave. It is a transverse wave. We just know, because remember, longitudinal waves are drawn like this. And then you have areas where they are compressed and something like this. So this is a diagram of a longitudinal wave. This diagram that looks like a sine and a sinusoidal curve is a transverse wave. The one thing about a transverse wave is that a transverse wave, the particles of this transverse wave, so if we were to take a small particle here, you will see, and we track its movement with respect to time, you will see that that particle is here initially, then it goes up and comes back. So it's change in position. It's in the, let's say it's in the y-axis. However, the direction of the whole wave is actually moving, as they said, from left to right. And now if you check, the angle between there is 90 degrees. That's why we say it is a transverse wave. The direction of displacement of the particle, or the change in position of this particle, is in the y, or the vertical direction. However, the direction in which the whole wave itself is moving is in the direction perpendicular. It is in the horizontal direction. That's what we describe as a transverse wave. So, question 3.1. Are we done? We're just analyzing this diagram. I think for now we are. What type of wave is a water wave? So we are told that this diagram represents a water wave, and we've already demonstrated and explained that it is actually a transverse wave. So we'll just write there that the water wave is actually a transverse wave. Write down the amplitude of the wave. So an amplitude refers to, this is question 3, an amplitude refers to the maximum displacement. So I said that you have a particle, and as this wave sweeps through it, it jumps, woo, and then it will also come back down. So that makes it, remember, it jumps from equilibrium to a highest point there, the crest. And then it will, after the wave has swept through it, as the wave is moving from left to right, it now comes down. So the amplitude is actually the maximum, it's the magnitude of the maximum displacement from equilibrium to the highest point. If this dotted line, for us, we decide that this dotted line represents equilibrium, and this particle is displaced from equilibrium, jumps there, reaches that point. So that maximum displacement from equilibrium to the highest point, which we call the crest, means we need to find what is this distance here, or what is that displacement, how much is it. We're not given that value, but somehow we are given the value from the trough, so D and H represents the trough, the lowest points on this wave, to the crest. So we're given this distance here from crest to trough, and that is given as 2.5 meters. Now the amplitude, I said it is that maximum displacement, is the magnitude of the maximum displacement from equilibrium to the highest point. But also you and I can agree that this distance, or this distance from here, equilibrium to the crest, is the same distance from equilibrium to the trough, right? Those two distances are the same. And if those two distances are the same, it means to find the amplitude, I can just simply say it is that total distance from the trough to the crest, which is 2.5, divided by 2, which will give me how much? 2.5, I think, is going to be 1.25. So I say it's going to be 2.5 divided by 2. So that is 1.25. Let me minimize this calculator. So it means write down the amplitude of the wave. You're just gonna write 1.25 meters because of how I've just explained it. And now we need to define the term wavelength. So how do we define a wavelength? A wavelength can be defined as the distance between two consecutive, or between two successive crests. The distance between two consecutive, did I get the spelling wrong? Two consecutive crests or troughs. Or sometimes this is just defined as the distance between 2 points on a wave that are in phase, between the distance between 2 points in phase. I'll just explain what these two things mean. So we'll say, so I get the spelling for consecutive. Is it a U? Is it a U? Two consecutive. Is that it? Is it written with a U or an A? You'll just check for me. The distance between two consecutive crests or troughs, or sometimes it can be defined as the distance between 2 points in phase. So if we go above at our transverse wave, this distance here, let me try to erase because now I've made a mess. So remember the trough and the crest. The crest means the highest point on a wave, and the trough means the lowest point on that wave. Okay, I'm done. So if this is the crest, this is the highest point on this wave B, this is the highest point again F, this is also the highest point J, meaning all of these points are crests. This is the lowest point on this wave D, this is another lowest point on this wave H, so that those are troughs. D, H. The crests are what is it? B, F, J. B, F, and J, right? The distance between two consecutive crests, two crests that follow right after the other. That is the right English. So this distance here is a wavelength. Also, this distance here from F to J is a wavelength as well. So the distance between B and F is equals to the distance between B, F, and J. And now this distance also between D and H is also a wavelength, lambda. So this letter is the Greek letter lambda. Additionally, we also said that the wavelength can be defined as the distance between 2 points on a wave that are in phase. And two points are in phase. It means that they are separated by a whole number multiple or an integer multiple of wavelength. So if you have 2 points on a wave and you say the distance between these 2 points is either 1 times the wavelength, depending on what the wavelength is, or 2 times the wavelength, or 3 times the wavelength. So it's an integer multiple or a whole number multiple of wavelengths. Those points we also say when they are separated by a whole number multiple of wavelengths, we say that that represents those 2 points are in phase. So let's see, point A and point C. If you look at the distance between point A and C, you can agree, even if you took a ruler, that distance is also equals to the distance between B and F. So it means also the distance there is also a wavelength. Also between E and I, that distance is also a wavelength. That tells us that those points they are said to be in phase because they are separated by one wavelength. Point A and I also in phase because they are separated by 2 wavelengths. I hope that makes sense and that I've convinced you of my explanation. So you will get your 2 marks for mentioning that it is either the distance between 2 consecutive crests or troughs or the distance between 2 points on a wave that are in phase. And then the next question says, determine the wavelength of this wave. How much is the wavelength of this wave? It doesn't say calculate, it just says determine. It means we can get it from the graph. We have agreed that the distance between points B and point F is a wavelength. So the distance here is a wavelength. We are only, however, given the distance between B and D. But you see that the distance between B and D is equals to the distance between D and F. So it means also the distance from here to here is also 1.5. So what is that telling us? It tells us that the wavelength lambda is going to be equals to 1.5 plus 1.5, which is equals to 3 meters. Not sure why that question is worth 3 marks. But essentially that's how you will get your 3 marks. I think also show how you got to that point. It's just 1.5 plus 1.5. So that is our wavelength, lambda. Then another question says, name 2 points on the wave from above that are in phase. So I explained a bit briefly about points in phase. Points that are in phase are points that are separated by a whole number multiple of wavelengths. So separated by either 1 wavelength, 2 wavelengths, 3 wavelengths, 10 wavelengths, up until whatever, right? So you just need to select one. So you can just say, okay, points A and E, because they are separated by 1 wavelength or 1 complete wavelength, are in points. Or somebody might say, Points F and J are separated by one wavelength, so they are also in phase. So it really, the choice is yours. So you can just say A. The memo will give all the correct options. So A and E. Then you get your 2 marks. A and E, correct. So now we need to calculate. It says calculate the time taken for 4 crests to move past a certain point in the path of a wave. 4 crests. So we said the highest point at the crest, we have the crest B, we have the crest F, we have the crest J. So I'm just going to try to mentally, I want you to mentally extend this wave so that we can add another crest. So something like that. So you say we have another crest here. So if we have 1, 2, 3, 4 crests. So they say those 4 crests, we need to, the time taken for those 4 crests, or calculate the time taken for 4 crests to move past a certain point. So 4 crests, how do we determine that time? From the question statement, we are told that the time between 2 consecutive crests is 0.5 seconds. So it means the time from here to here is 0.5. That is the period. The time from here to here is also 0.5. And then the time from here to here is also 0.5. So we just need to add all of that. So one thing is that you see if we have 4 crests, or maybe we even had 4 troughs, would have how many full wavelengths? How many full waves? So this is a full wave, this is another full wave, and this is another full wave. So we have 1, 2, 3 full waves. And the time to complete one full wave is just 0.5. So to determine that time taken, so we just write T equals to 0.5 times 3. How much is that? If we put it on a calculator. So here's my calculator. We have 0.5, that's going to be 1.5, I think. It's going to be 1.5. So we have 1.5 seconds. That's how you get your marks. And then we have to now calculate or to determine the speed of the wave. There's always a number of ways that you can solve these types of problems, but I'll just show you one. So we can use the wave equation V equals to the frequency F multiplied by lambda. This is the speed, this is the frequency of that wave, and this is the wavelength. Because why? We have the wavelength, we determined it somewhere. We said it's I'm lying, it is 3 meters. We have the frequency. Do we have the frequency or am I lying? We don't have the frequency, but we know the period T, which is 0.5, which is the time taken between 2 consecutive crests, or the time taken between 2 consecutive troughs, or the time taken to complete one complete wave. And that period T equals to 0.5 seconds. Now, how on earth are we going to solve using this equation? The nice thing about the period, I spoke about this earlier, is that there's actually a relationship between the period and the frequency, and it is that the frequency is the inverse of the period. F frequency equals to 1 over capital letter T. So it means in here, I can just write 1 over T, so that we only have V for the speed equals to 1 over T. You can put it in bracket, lambda. And this will just be lambda over T. What is my wavelength? 3. What is my period? 0.5. So 0.5 is a half, so 3 divided by a half, that is just going to be 6 meters per second, or somebody might write it meters dot second minus 1. So you'll get a mark for the formula. Then I think you'll get a mark for this, for the correct substitution and the final answer. If you don't get a mark for this stage here, you might get 2 marks for the answer, because you wrote both the magnitude and the unit of measurement. So let's go to question 4. Question 4. A sound wave is produced by a source placed at a certain distance from a building as shown below. The echo reaches the source after 8 seconds. The speed of sound in air is 340 meters. So we are given the value for V. So what do they say? A source makes a sound. That sound travels, goes to the building, is reflected off the building, meaning it comes back, and then it reaches the source after how long? The time is going to be 8 seconds. Right? And we know the time like that. So 4.1.1. Sound is a type of a longitudinal wave. That's why the first question there just tells you to define a longitudinal wave. Define the term longitudinal wave. A longitudinal wave is a wave in which the particles of the medium vibrate, or somebody might say propagate, or displaced, vibrate parallel to the direction of motion of the wave. Go back of the wave. So this is in contrast to a transverse wave, which we dealt with earlier. So with a transverse wave, we say the particles are displaced in the vertical direction, but the whole wave is moving like this. Hence, there's a 90-degree angle, or they are perpendicular. But with a longitudinal wave, the wave is moving in this direction, and the particles are also displaced in that direction. Hence, we say it is a longitudinal wave. So that sound will be traveling in that direction towards the building. Now, calculate the distance. 4.2, calculate the distance between the sound source and the building. So we need to determine this distance from the source. Let's say it's from here until the building. Let's call that distance. You can just say distance. But I want you to note that the time that we're given is the time from the source to the building, then back. Does that make sense? So if we say that we know that the formula for distance is just the distance typically is equals to, what is it? The distance is equals to the speed multiplied by the time. But we want the distance here from the source to the building, but we're given the time from the source to the building back. It means that it took half the time to move from the source to the building, right? So you can just say the distance in this instance is actually 2 times the distance, 2 multiplied by the distance, because that sound traveled this distance towards plus this distance back, so that it can be detected there at the source. And the speed of that sound was 340 multiplied by the time, the total time it took to move to the source and then get reflected at the building back to the source. The time was 8. And then to make distance the subject, we just divide both sides by 2. What you do on the right, you also do on the left. As mathematics. So this 2 will cancel this 2, such that we have that the distance equals to 340 multiplied by 8 divided by 2. Let's put that in a calculator. Say we have 340 multiplied by 8 divided by 2. How much is that? 1316. 1316. Ooh. Can we just win disappear? Let me click here. Okay. So the distance is actually 1360 meters. So that is the distance from the source to the building. Isn't it interesting that we can just determine the distance from knowing the speed of sound and the time? That is an interesting property of sound. So we've done 4.2, 4.3. Name the property of sound that influences its pitch. We spoke about this earlier when we said that property of sound is the frequency. The frequency is related to the pitch. The loudness is related to the amplitude. The tone or the quality of sound is related to what? So those are the properties of sound, the pitch, the tone, as well as the, what else? The pitch, the tone, as well as the loudness. Above which frequency is a sound wave classified as an ultrasound? So where sounds with very high frequency are called ultrasound. So if a sound wave has a frequency above 220 kilohertz, we say that sound is ultrasound. Somebody might write 20,000 hertz because kilo means 1,000. So you still get your mark. And ultrasound is actually used in medicine when people go to take their ultrasound scan when they are pregnant. They use that property of sound to be reflected. So name one use of ultrasound in the medical treatment of patients. You can say to examine the process or the progress of an unborn child during pregnancy. It can also be used for physical therapy or to sometimes diagnose, because we are able to form an image of the internal structures in the human body using ultrasound. So you can just say one, diagnosis of a medical condition or examination of a baby, of a child during the mother's pregnancy. Some people who are interested in studying radiography after matric, they will learn about ultrasound imaging. It's very interesting. Question 5. The frequency and corresponding energy of electromagnetic waves are given in the table. So we are given a table. We have wave A, B, C, D, E. We're given the frequency in hertz. It's always important to check. Is it in hertz? Is it in kilohertz? We're also given the energy in joules. So these are the correct SI units. 5.1. Describe how an electromagnetic wave propagates. So typically, I hope I can draw this nicely. So in electromagnetic waves, typically you have the electric part of it and the magnetic part of it. So if the electric part of it is like this, the magnetic part of it is going to be perpendicular to this. Let me show you how. And then you have, my hand, my writing is going to be like, yes, something like that, right? So these two will be perpendicular. I know my handwriting, my drawing is not perfect, but Hopefully you're starting to see the picture. So these two, the electric component, so that is the magnetic component in red, the magnetic component and the electric component are perpendicular. So if we define it, we would then say that an electromagnetic wave propagates as an oscillating, it means a changing, oscillating electric field. Electric field in one plane, right? And which produces an oscillating magnetic field at right angles, or sometimes somebody might say perpendicular to it. We'll memorize that. An oscillating electric field in one plane produces an oscillating magnetic field perpendicular to it. Did I get that wrong? Perpendicular to it. Somebody might say an oscillating magnetic field or a changing electric field in one plane produces a changing magnetic field at right angles to it. Now we are asked to, what is the relationship between frequency and energy of an electromagnetic wave as shown in the table? So if we look at the table, you will note something. So in the table, we have the frequency. So we have 2 multiplied by 10 raised to the power of 9, 4 multiplied by 10 raised to the power of 4, 3 multiplied by 3.5 multiplied by 10 raised to the power of minus 15. This one is raised to the power of minus 18. It means that as we move from A to F, the frequency is increases. Let's check the energy. The energy we have minus raised to the power of minus 24, raised to the power of minus 21, raised to the power of minus 18, up until raised to the power of minus 14. Minus 14 is greater than minus 24. It means also the energy is increasing. So what is that relationship? How do the two quantities relate? So the two quantities relate that as the frequency of the wave increases, let me just go down a bit. As the frequency of the electromagnetic, I don't need to write down. As the frequency increases, the energy increases. Or this type of relationship, we can just say that the frequency is directly proportional. Directly. How do you write directly? How can I forget that? The frequency is directly proportional to the energy. Left the C here, directly proportional to the energy. And you'll get your 2 marks. Let me just move this up. Ooh, technology. Now we go to question 5.3. Calculate the frequency of wave E. Frequency of wave E, we're not given the frequency, we are given the energy. So we need to calculate the frequency. So one way of doing this is that we can just use the equation for the energy of a photon, which is E equals to HF. You can draw this triangle over here. Nope, it's a mistake. Draw this triangle over here. I'm like, okay. I think my mind is tired now. So we say E equals to HF. But we want to calculate the frequency. So to make the F the subject, we just say F equals to E is at the top in the numerator, H is at the bottom, meaning it will be at the numerator. So the nice thing is that this is a constant that is provided to us, H. It's called Planck's constant. You can just go down. If you go check in your formula sheet, you'll find that constant there. There it is, H. And it's given by 6.63 multiplied by 10 raised to the power of minus 54 joule second. So that is what we will use. We know the energy, we know Planck's constant. It means we can actually calculate the frequency. So here we are. The energy is 4.97 multiplied by 10 raised to the power of minus 14. Always put things in brackets when we are working with very large or very small number. We said it's 6.63 multiplied by 10 raised to the power of minus 54. How much is that? Where is our calculator? Oh. So we have a bracket 4.97 multiplied by 10 raised to the power of minus 14. This divided by 6.63 multiplied by 10 raised to the power of minus 54. What did I do? There's a mistake that I made here. I didn't take the bracket down, so I need to do that. So the answer is 7.496. Ooh, I closed that. So the answer is 7.496 or 7.49 multiplied by 7.496 multiplied by 10 raised to the power of minus 10 to the 19. So remember, our instruction mentioned that we need to write that our answer is 2 decimal places. So it's going to be 7.50 multiplied by 10 raised to the power of 19. You need to also include the SI unit, which is hertz. That does not make sense. Did I say 19? That makes no sense at all. Did I make a mistake somewhere? Okay, no, that actually does make sense, because 10 raised to the power of 19 is actually greater than 10 raised to the power of minus 18. And we said that the frequency is increasing. So that is correct. So now we need to calculate the wavelength of D. The wavelength of D, there's many ways of doing this, but I'll use the simpler, straightforward way. So one of the equations for the speed of an electromagnetic wave in vacuum is C, which equals to F times lambda. And also draw a triangle for this, where C equals to F lambda. We need to find the wavelength lambda, so it's C in the numerator, C is at the top, and F in the denominator, F. C, we know it's a constant. You can always double check at the end of your question paper, and you find that C is actually 3 multiplied by 10 raised to the 8. So C equals to 3 multiplied by 10 raised to the 8 over F. What's the frequency of D? The frequency of D is actually 1.8 multiplied by 10 raised to the 18. So how much is that going to be? 1.8. So it means that the wavelength is going to be equals to 3 multiplied by 10 raised to the 8, close that bracket, 1.8. If you're working with very large numbers, it's very important to open those brackets. And how much is that? That is 1.6. Is it 1.66? So it's going to be 1.67. So 1.67, two decimal places, multiply by 10, raised to the power of minus. So it is minus 10. Yes, it's minus 10. And it's in meters. The last question for question 5. Which wave A or B has a higher penetrating ability? So in terms of higher penetrating ability, if a wave has a higher frequency or a higher energy, it means it has a higher penetrating ability. So wave B has a higher frequency and a higher energy than wave A. It means that the answer is A. Why? Because it has A, you can just write, has a higher energy, or higher frequency. So the higher the energy or the higher the frequency, the higher the penetrating ability. Question 6. I think this is the longest video I've ever done. Question 6. A small metal sphere A carrying a charge of positive 2 multiplied by 10 raised to the power of minus 9 coulomb is placed on an insulated stand. So there is the charge. How does the number of electrons compare with the number of protons in sphere A? Because it's positively charged, we know that the number of electrons are actually less than. So you just write less than. It means it has a shortage, it has a deficiency of electrons. So it has more protons than electrons. And now they say 10 to the power of 13 electrons are now added to sphere A. So we take electrons, we put them in sphere A. When you need to calculate the new charge on sphere A, that is 4 marks. So how do we do that? So we will say, we will use an equation for the charge. Is a charge quantization. The charge quantization equation says N equals to QE, where N is the number of electrons which you are given and QE is the charge on a single electron. That value is actually a constant as well. If you check at the back of your question paper, it's 1.6 multiplied by 10 raised to the power of minus 19 coulombs. You can always double check just to make sure what you are given. There it is. It is minus 1.6 multiplied by 10 to the power of minus 19 coulombs. If you are dealing with protons, that number is going to be positive. But for now, it's negative because we're talking about electrons and they carry a negative charge. So we have N, we also have QE. It means that N, they said it's 10. They said 10 to the power of minus 13 electrons were transferred to this charge A, were added. In a way, minus 1.6 multiplied by 10 raised to the power of minus 19. To put this in a calculator to find out how much. So we get given the electrons. So we want to see how much charge was actually transferred. The charge will be Q. So we have 10 raised to the power of 13 multiplied by minus 1.6 multiplied by 10 raised to the power of minus 19. I like using brackets. It just helps to keep in check, to make sure that I don't get the incorrect value. Was it minus 6? It's 1.6 multiplied by 10 raised to the power of minus 1.6 coulombs. So it means this amount of charge was transferred to this. What is the new charge? We'll say, okay, the new charge will be Q nu, which is equals to the initial. So whatever was in that sphere was plus. Don't need to write plus. I'm just writing it to show that it was positive, minus 9 put it in a bracket, plus minus 1.6 multiplied by 10 minus 6. Always also put it in bracket. So how much is that? So our Q new will be how much? So we'll say brackets 2 multiplied by 10 raised to the power of minus 9 plus, right, plus 1 point, I'm lying, it's a negative 1.6. So you know a positive multiplied by a negative is always is always a negative. I'm just including all the steps because I don't want for people to make a mistake. So put it as it is. Put it as it is in there. And we are now, that value is 1 point, what did I do? That value is minus 1.598 multiplied by 10 raised to the power of minus 6. But we know, our question told us that we need to write this to two decimal places. Well, minus 1 point, if it's 1.59, it's going to be 1.60. So this is actually 1.60 multiplied by 10 raised to the power of minus 6. So that will be the new charge on this sphere. It's no longer going to be 2, it's going to be minus 1.4 on 1.60 multiplied by 10 raised to the power of minus 6 after we add the electrons. So now it has an excess of electrons. So that is a 4-mark question. You see, you start with the charge quantization expression, and then you just add the two charges to each other. Now we have two identical metal spheres, B and C, as they are shown here, placed on insulated stands, and they carry charges of 4 multiplied by 10. So this is the charge here. Okay, let me not do that in case I need to use that space. So the charge on B is plus the positive 4 multiplied by 10 raised to the power of minus 6. It tells us that this sphere has a shortage or a deficiency of electrons, and the charge on sphere C is minus 6 multiplied by 10 raised to the power of minus 6. It means it has an excess of electrons. And now the spheres are allowed to touch. As you can see, here they are touching. After touching, the spheres are then separated and brought back together to their original positions as shown in the diagram. So there they are, they have separated. Now we need to state the principle of conservation of charge. So that principle, go memorize it. It tells us that the net charge of an isolated system remains constant. Sometimes when things are said in this way, they feel a bit cryptic and you can't really interpret what they mean. But essentially what they tell you that during any physical process, if you consider that system isolated, their charges, the total charge remains the same. Before they touch, this is before, and after they charge. If you add the two charges before and after they touch, it will really remain the same. And this is irrespective of that after these two spheres touch, the charges on each sphere changes. The total, the net charge in that system remains the same before touching and after charging. So we've done that. We got in our 2 marks. It says now calculate the number of electrons transferred between the two spheres during contact. Carries a lot of marks. It's like 6 marks. How do we do that? So first, our equation for the charge, the conservation of charge, will say Q equals to Q1 plus Q2. Tell you what it means now. And we can just rewrite it as QB plus QC all divided by 2. But this equation tells us that the new charge, this is the new charge after touching on each sphere, will just be equals to the net charge of so the sum of this the charges before divided by 2. What is this telling me? It means that the charge after touching will be Q on both spheres, whatever value of Q that is. It means the charges we'll see will be the same. They will have the same charge after touching, because the charges would have been transferred. So it means we need to find first the new charges. So we say, okay, Q will just be Q, the charge on B. How much is that? It is 4. It's a positive 4 multiplied by 10 raised to the power of minus 6, plus the charge on C, which is a negative 6 multiplied by 10 raised to the power of minus 6. Let me double check if those are the correct values. Yes, positive 4 multiplied by 10 raised to the power of minus 6, and minus 6 multiplied by 10 raised to the power of minus 6. Then we divide that by 2. And we need to find the new value. Brackets are your best friend. Always put those brackets in. They help keep track. 4 multiplied by 10 raised to the power of minus 6 is plus minus 6 multiplied by 10 raised to the power of minus 6, all divided by 2. And we get that the minus 1 multiplied by 10 raised to the power of minus 6 coulomb. This is telling us that the charge now is minus 1 multiplied by 10 raised to the power of minus 6 C coulombs. Even here it's minus 1 multiplied by 10 raised to the power of 6 coulombs. That is the new charge after a physical process, after they touched. But the question didn't ask us to determine the new charge. It tells us to calculate the number of electrons that is transferred. So typically the negative charges, the electrons are the ones that are transferred. It means this charge here will transfer a part of its electrons to this charge here so that they are equal. So the charges are transferred from C to B. Now, how do we find the charges, the amount of charge that is transferred? We can use a formula. I don't think this is given at the back of your question paper. Let me go check. I don't think so. I've never seen it. You see? Under electrostatics, you're only given the formula for the charge quantization. I said it's QE. They write E, it's the same thing. And you're also given the formula for charge conservation. So that thing, you say the change in Q equals to the final charge on whatever sphere B, because that's where the charge has been transferred from. It's been transferred to, so we want to see how much charge was transferred. If we know how much charge was transferred, we'll know how many electrons. So Q, change in Q is going to be QF. QF, the final charge on that sphere after touching was 1 multiplied by 10 raised to the minus 6. The initial charge on that sphere was just 4 multiplied by 10 raised to the power of minus, how much was that? Raised to the power of minus 6 as well. Let me double check. So that was it on B. Yes. So we put this in a calculator. We have minus 1 multiplied by 10 raised to the power of minus 6 minus 4 multiplied by 10 raised to the power of minus 6. How much is that? It is 5. It's going to be minus, I wonder what's going on. What is this thing loading? Minus 6. So my calculator is gone. So the change in Q is going to be minus 5 multiplied by 10 raised to the power of minus 6. We are asked to calculate, is the space where I can calculate this? No. We are asked to calculate the number of electrons. From this charge quantization formula, we know that Q, so where is it? The charge quantization formula is equals to Q equals to NQE. So meaning I can write Q equals to NQE. I want to calculate N, to determine N. And this means that my N is going to be given by Q is at the top, the numerator Q divided by QE. So we see for us that Q is actually just going to be the change in Q, because we are interested in the electrons that are transferred, which we determined as the change in Q, and that change in Q is minus 5 multiplied by 10 raised to the power of minus 6 divided by the charge on one electron. It's a constant, 1.6 multiplied by 10 raised to the power of minus 19. How much is that? So that is going to be, let's see, brackets, minus 5 multiplied by 10 raised to the power of minus 6 divided by minus 1.6 multiplied by 10 raised to the power of minus 19. So that is going to give us 3.13, because we are interested in 2 days. 3.13 to the power of 13. 3.13 multiplied by 10 raised to the power of 13 electrons. So that is the amount of electrons that are transferred, and that's how you get your 6 marks. So quite a long question, but it's interesting to solve. Finally, question 7. Consider the circuit diagram below. So in your circuit, you have a voltmeter, V1. That's a voltmeter. You have a switch S, which is switch S, there it is. You have a battery with 24 volts. You have an ammeter A1 there. You have another voltmeter V1 that is connected across a light bulb. Measures the potential difference across that light bulb, and that light bulb has a resistance of 8 ohm. And then you have these 2 other light bulbs here that are connected in parallel to each other, and they have a resistance of 8 ohm each. You also have ammeter. This ammeter will measure the current through this light bulb, and this ammeter A3 will measure the current through this light bulb. So switch S is open. There it is, that's a switch that is open, means the circuit is incomplete. Write down the reading on the following. So the reading on voltmeter V1, when that switch is open, it's still going to be 24, because that voltmeter V1 will register the EMF of the battery, which is 24 volts. And the reading on ammeter A1, it will be 0, because if this switch is open, it means the circuit is incomplete, and what that means is that there is no flow of charge. If there is no flow of charge, it means there is no current. There's no current in ammeter, which measures the current either in a circuit or in a circuit element, can't read anything. There's no current. When we close that switch, we are told to calculate the equivalent resistance. Before we continue with this question, I'm not sure if you'll be writing on equivalent, how to determine the equivalent resistance, because according to your ATP, that is actually for the second term. But I'm going to show you how, just in case. Okay, so to determine the equivalent resistance, we'll say, okay, this circuit, why am I saying a circuit? This light bulb is connected in series. but these two are connected in parallel. So we first need to determine the parallel 1 over Rp, if the resistance of the parallel connection. And it's going to be 1 over R, 1 over 8 plus 1 over 8. So remember, typically that formula, I'm not sure if it's there at the back of your question paper. Let me go check. That's the memorandum. You see, it's 1 over Rp equals to 1 over R1, 1 over R2. So this is the formula that I'm using. So the resistance on that light bulb, the first light bulb, is 1 over 8, and the other one is 1 over 8 as well. So you just say 1 over 8 is just going to be 1 over 4. If you put that in your calculator, 1 over 8 plus 1 over 8 is 1 over 4. 1 over Rp. So to find Rp is just a matter of inverting this. So Rp goes to the top. This means what you do on the left, you do on the right. So you also have Rp equals to 4. I'm sorry if I'm going a bit too fast now. I'm getting a bit tired. So it means that the resistance, if we were to replace these two, the effective resistance here on this parallel connection is 4 ohm. But now it means that we can find the total resistance there as the resistance for the serial connection, we call that Rs, plus the resistance for the parallel connection, we call that Rp. So it's going to be 8 plus 4, which is 12. So our effective resistance Rt is going to be just 12 ohm. Let us now determine the reading on a voltmeter V2. There's a number of ways to do this. Some people will use Ohm's law, but I personally like to use this method because it just makes more sense to use it in terms of how to interpret a circuit diagram. So we want to find the potential difference that will be measured by this voltmeter V2. Remember, they are connected in parallel. It means they will experience the same potential difference. That is why voltmeter V2 will be able to tell us the exact potential difference across that light bulb. So how I like to do it is that I will say, okay, the total voltage or V1 is, we are told that V1 equals to 24 V, right? And the total effective resistance is also RT, which is 12 ohm. These two connections will split. There will be potential dividers because they are connected in series. The 4 ohm resistor, which represents the parallel resistance, and the 8 ohm resistor. So if that is the case, it means the ratio in which they split the potential difference is 8:4. What do I mean? It means I can just say V2 is going to be V1, which is the total potential difference, multiplied by the resistance on that or light bulb, which is 8, divided by the total resistance. So how much is that? V1 is 24 multiplied by 8 divided by 12. So 12 divided by 24, that is 2 times 2, that is going to be 16 volts. So you'll get a mark for writing that out. Now, question 7.4. How do the readings on ammeter A1 and ammeter A2 compare with each other? Let's look. So we have ammeter A1 and A2. So you will learn that resistors connected in parallel, they will have the same potential difference. However, they will split the current. But it means they will have a current going through this, and then you'll have another current going through the other branch. But because these resistors are the same size, it means they will have the same current. So if the current going through here is 1 ohm, is 1 ampere, the current going through this one will also be 1 ampere. So it means that they will be the same. So you can just write they are the same. The same. So they will do the ammeters there will measure the same current. The graph below shows the relationship between resistance and the length of a conducting wire. There is a graph. We have the resistance on the y-axis. And then we have the length of wire in millimeters on the x-axis. So this is the independent variable. That's what we are changing. And we're seeing that as we change, as we increase the length of that wire from 0, 10, 20, 30, 40, 50, 60, 70, the resistance also increases to from 0.5, 1, 1.5, 2, 2.5, 3, 3.5. As the one increases, the other one increases. It's a directly proportional relationship. And question 7.51 says, what is the relationship? Write down the relationship between the resistance and the length of the conducting wire. We said that as the resistance, as the length of wire, as the length of the wire increases, the resistance increases. Or somebody might say the length of wire, the length of the, say the length of the conducting, because that's what they said, conducting wire, the length of the conducting wire is directly proportional to the resistance. Right? So you get your 1 mark. Determine the resistance of wire with a length of 30 millimeters. So here is just a matter of, I wish I had a ruler. It's just a matter of saying, okay, 30, there's 30. I wonder if I'll be able to draw in a straight line. Trying to get to that point somewhere there. Ooh, that is not a straight line. But if you look, it's somewhere here, and then you check the what is it? Ooh, my English has disappeared after 2 hours of talking. You will check the corresponding resistance values between 1 and 1.5. So I may say, if when you're writing, you'll have a ruler. So just check. So that value is going to be around 1.35 ohm, right? And you'll get your 2 marks. This is an important thing because resistance has a relationship between the length of a wire, the temperature. What else? I've forgotten the other thing. I have a headache now. But anyway, we've come to the end of this question paper. I hope you found it helpful to help you in preparation for the upcoming March control test. So what the last thing that I want to say is that, so you are given about 2 hours, which is 120 minutes to write this paper, and it's 100 marks. So typically this means if you spend, let's say for each, so it means 1 minute, 1 mark. It means that after 100 minutes you'll be done, and you actually have an additional 20 minutes to check your answers. It's always important to go back and check. Maybe you missed something, maybe you misunderstood something, and then now you're going back to it. So 1 minute, 1 mark strategy. If a question is 2 marks, it means you can only spend about 2 minutes. That's the strategy that I used when I used to be a learner of physical sciences. Anyway, I hope you found this helpful. If I made a mistake somewhere, please let me know. Please let me know. Also tell me your feedback. How did you find some of the concepts that I explained? What is it that you struggled with? What it is that you found interesting? Thank you so much.